You recognize carbohydrate as being a nutrient, something that's in food. We're going to look at the chemical structures of the carbohydrates. The early chemists found that the empirical formula of all of the simple carbohydrates was 1 carbon to 2 hydrogens to 1 oxygen. And because that looks like carbon with water attached, they called them hydrated carbon or carbohydrates. The formula or the structure is actually a little bit more complicated than this, but let's start with this. All of the simple carbohydrates have "ose" on the end, and so you can recognize from the name what is a carbohydrate. Glucose, fructose, mannose, all of those are carbohydrates. The carbohydrates can be classified if it's a pure carbohydrate, nothing attached to it besides the carbohydrate. You can classify it as a monosaccharide, a disaccharide, an oligosaccharide, or a polysaccharide. Monosaccharides have 1 sugar unit in them. Disaccharides are 2 sugar units attached to each other. Oligosaccharides are a few sugar units attached, and then polysaccharides are bunches and bunches and bunches, long chains of them attached together. All of these are water soluble except for the polysaccharides, and the reason that they're so not water soluble, they're usually water suspendable, is because the molecule is huge, and such a huge molecule is not water soluble. The monosaccharides all have that empirical formula that we talked about of CH2O. But you don't have any monosaccharide that has this particular formula. The smallest is 3, and they range up to 6. We identify or describe a monosaccharide based on how many carbons it has. So triose, tetrose, pentose, hexose is all just telling you how many carbons. The functional groups that are on the monosaccharides is a carbonyl that is either an aldehyde or a ketone, and then all the remaining carbons that don't have the carbonyl, the ones that do not have the carbonyl on them, all have hydroxyl groups attached. So the aldehydes we call aldoses, and the ketones we call ketoses, and we'll smash it all together with the description of number of carbons and call them things like aldopentose or ketohexose. So every carbon in the structure has an oxygen on it. 1 has a double bond to an oxygen. The rest are all hydroxyl groups. So here are 2 different monosaccharides. This one is an aldohexose. This one's a ketopentose. You see, this one has the carbonyl, and then every other carbon in the molecule has hydroxyl groups on it. Here, this is a ketone. The others, all the other carbons, have hydroxyl groups on them. So you have to be able to recognize an aldehyde, and you have to be able to recognize a ketone. Remember that aldehydes have the carbonyl at the end of a chain, and a ketone has a carbonyl in the middle of a chain. You can also look a carbonyl that has a hydrogen attached is an aldehyde. A carbonyl that has a carbon on either side is a ketone. So go ahead and look at this and try to classify this type of monosaccharide here. And when you're through with that, just draw an aldotetrose. What would it look like? Okay, this is the ketopentose. You see, this is a ketone because there's a carbon on either side of the carbonyl. And then there are 1, 2, 3, 4, 5, so it's a ketopentose. To draw an aldotetrose, you have to have 4 carbons. One, either this one or this one, it doesn't matter which, has to have a carbonyl on it, but it has to be the end carbon. This end carbon or this end carbon. Doesn't matter which way you draw it. Then all the remaining carbons have to have hydroxyl groups on it, And then you have to fill in the hydrogens to make every carbon have 4 bonds. If you look at the alcohols that are in monosaccharides, you will see that some are primary and some are secondary. There are no tertiary alcohols. Now, what is a primary, secondary, and tertiary alcohol? A primary alcohol, you see there's 2 hydrogens attached and only 1 carbon attached. Here, secondary, 2 carbons attached, only 1 hydrogen attached. Now, what am I looking at? I'm looking at the carbon that has a hydroxyl group on it. So, identify the hydroxyl group, move to the carbon. 2 hydrogens and a carbon, that's primary. Identify the hydroxyl group, move to the carbon. 2 carbons and 1 hydrogen, that's secondary. If there are 3 carbons on it, then it's tertiary, but you don't see this in any of the monosaccharides. Carbons that have 4 different groups are chiral. You've seen this before. And carbohydrates have chiral carbons. This is very important to their characteristics. The carbonyl, of course, cannot be chiral because anything with the double bond is not chiral. And primary alcohol carbons are not chiral because they're going to have 2 hydrogens attached. But all the other carbons are chiral. And this is very important. If we go back and look at this structure, not chiral, 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 not chiral. Not chiral is primary, not chiral, carbonyl. Chiral, chiral, and then not chiral because it has 2 hydrogens attached. So in this molecule we have 4 chiral carbons, and this we have 2 chiral carbons. We designate both amino acids and carbohydrates as being either D or L to designate what's going on with the chiral carbons. Now, it's only one particular chiral carbon in the molecule that we look at. Whenever we write our monosaccharides, we commonly put the carbon chain in an up and down fashion, and we put the carbonyl closest to the top of the page. What we do is look at the bottommost chiral carbon, and the position of that hydroxyl group tells us whether it's D or L. This is L-glyceraldehyde. It's the simplest monosaccharide there is. This is an aldotriose. This is an aldotriose. This is L-glyceraldehyde, D-glyceraldehyde. What we do, though, is we don't draw them like this. We draw them in the up and down fashion. So here is transforming it to an up and down fashion. I'm twisting this so that I have the hydrogen and hydroxyl on either side coming out at you. And then what you see is hydrogen on the left and hydroxyl on the right. That's the D conformation, and we call this drawing a Fischer projection. Almost all of the biologically available carbohydrates are D monosaccharides. So you write the carbonyl closest to the top, and at the bottom you look one up from the bottom, and if the hydroxyl is on the right, then it is a D sugar. L sugars don't occur, maybe just in some real isolated instances, but 99.99999% of all carbohydrates are D conformation. So when I draw them in the Fischer projection, how I go and I recognize that the carbonyl is written at the top. I go down to the bottom and go one up. Why do I go one up? Because this is not chiral. Go one up, and I look at the conformation and see if the hydroxyl is on the right or the left. If it's on the right, it's D. If it's on the left, it's L. So let's look at glucose. Here is the structure of glucose, and I don't expect you to be able to draw this, but you be able to identify the classify the monosaccharide. So if I look at this, I see this is a hexose, and it's also an aldose. And if I look at these, I can see it goes right, left, right. And so these are chiral carbons, but this is the one I want you to focus on. The hydroxyl is on the right, so it's a D sugar. This is D-glucose. You will often hear of dextrose. That is another name for D-glucose. If I look at fructose, fructose is an aldose, ketose, and it is 1, 2, 3, 4, 5, 6 carbons, one up from the bottom. You have the hydroxyl on the right, so this is D-fructose. If I look at ribose, D-ribose, you will see that ribose is a pentose and it's an aldose. These are the 3 chiral carbons. The bottom one is on the right, so it's D. Ribose can be modified in biological systems to remove the oxygen and make it a deoxyribose right there. That is the deoxyribose that is in DNA. Ribose is what's in RNA. Now, carbohydrates, simple carbohydrates, the monosaccharides, do not exist very much in this, what we call the open chain, the Fisher projection. Instead, what we usually do is we write them in a ring form because that's the way that they are incorporated into biological molecules, and that's in solution. This is what you would primarily find. This is only a temporary state. When the monosaccharide forms a ring, the way that it occurs is this oxygen goes around back and comes and attaches to this carbon. You can see this carbon right here is this carbon. This carbon right here is this carbon. And because this oxygen could go around back or it could come around front and attach, there's 2 ways for it to close. Here is a D-glucose, and it's showing you that how to draw this in the Hayworth projection. You pull the top down to the right. Once you pull the top down to the right, this oxygen comes from behind. Notice this came from behind to push the hydroxyl down. But it could come from in front and push the hydroxyl up. So depending on which way it does, there's 2 orientations for this hydroxyl group. Those are called anomers. When the hydroxyl group, let's go back a slide, is down in the Hayworth projection, then it's called the alpha D-glucose for this one, an alpha monosaccharide. When it's up, it's called beta, and I remember this by saying BUP for beta up, and I'll remember which way it goes. So these 2 are the same sugar, but they're just in different forms, the alpha form and the beta form. Let me show you how to count the carbons. 1, 2, 3, 4, 5, 6. So this is a hexose, and I know it's D because in D you have the methyl hydroxy, the number 6 carbon is up, and that's what we see in all our biological systems. If I look at the carbon that's farthest on the right and I look at the hydroxyl is down, so this is an alpha sugar. If the hydroxyl is up, it's a beta sugar.